Okay, so now we're on 85.3, and we're supposed to demonstrate an understanding of the mean value theorem by applying it to the function f of x equals x to the 2/3. That's a funny looking x. On the closed interval from -8 to 27. Okay, so the function itself is continuous because we can take the cube root of -8 and square it is +4. We can take the cube root of 27 as 3 squared is +9. So it's continuous everywhere in between there, no problem. So the first part is met, but what about being differentiable? If we take the derivative of this, f prime of x is equal to 2/3 x to the -1/3, which if we write that without the negative exponent, it'll be 2/3 times the cube root of x. Well, the function is undefined if x is equal to 0, right? And 0 is in this interval. So is it differentiable everywhere on this closed interval? No, it's not. So the mean value theorem can't be used, period. Okay, going on to 85.4. It says the function f of x equals absolute value of x minus 1 is equal to 0 at x equals -1 and x equals +1. Does the mean value theorem imply that the first derivative of c is equal to 0 for some number between -1 and +1? Well, think about what that graph of absolute value of x looks like. Absolute value of x by itself would just be a v starting at the origin, but this -1 says that it starts here and goes like this. So that's what it looks like. So we're talking about on the interval from -1 to +1. Okay, is it continuous on that interval? Yes, it's continuous. Is it continuous on the endpoints? Yes, it's continuous. But what about the second part? Is it differentiable everywhere in this interval? The answer to that is no, because of this sharp corner right here. It's not differentiable at x is equal to 0. So the mean value theorem is not going to imply anything. So the mean value theorem does not apply. And that's true up here as well. Okay, now down at the bottom of page 437, it mentions that if the derivative of a function is equal to 0 at all the values of x, then that means that the function itself was a constant. So like if f of x is equal to 2, then yes, of course, the derivative is going to be equal to 0 everywhere. So then if you look on page 438, it's talking about, it says if the derivative of x, of f of x, and the derivative of g of x on a closed interval I are equal, if they're always equal, in other words, when you take the derivative of it, you get the same thing, then it just means that they differ by a constant value. So, like, if you get f of x, the derivative of f of x looks something like this. And the derivative of g of x, if it's equal to it, could look something like this, because the derivative is the slope of the tangent line, right? So if you get the same slope, then they just differ by some constant value. That's the only difference in the function, is this some constant value. So they're just parallel lines. All right, now down at the bottom of page 438, we're talking about Rolle's theorem. And it says if, number 1, f is continuous on a closed interval a to b, and number 2, f of A is equal to f of B, and it's equal to 0. So, in other words, we have some function, and it starts at 0 and it ends at 0, but it's continuous everywhere in between. Okay? So we have some graph, and that's the case. And if it's differentiable everywhere in this interval here, then there exists some number c somewhere in here. There's got to be a c. This is A and this is B, such that the derivative is equal to 0. Now, if the derivative means that's the slope of the tangent line, so somewhere in here, there's got to be a point where the derivative would be equal to 0. In other words, the tangent line would be horizontal. That's Rolle's theorem. Okay? So keep that in mind as we look on page 439. It says, the speed limit on a highway is 65 miles per hour. At 6 o'clock p.m., a police officer sees a truck go by at 60 miles per hour. That officer radios another police officer 70 miles down the highway, who sees the same truck go by at 7 o'clock p.m. traveling at 60 miles an hour. Okay, so between 6 o'clock and 7 o'clock, how much time elapsed? 1 hour. Well, the guy was supposedly only going 60 miles an hour, but the distance between police officer A and police officer B is what? It says 70 miles down the highway. So find the average speed of the truck between 6 and 7. Well, the average speed is total distance, which was 70, divided by total time, which is 1 hour. So his average speed was 70 miles per hour. If his average speed was 70, that means he probably went above 70 part of the way and below 70 part of the way. So let's see, what does it say? Find the average speed of the truck. We did that. This is the average speed of the truck. Letter B is, the truck driver is ticketed for speeding, but he argues that he was never clocked over 60 miles an hour. The truck driver is convicted by a judge who points out that he must have been traveling 70 miles per hour at least once. Is the judge correct? Yes, the judge is correct. Because if he if you have an average speed of 70 miles an hour and he traveled 70 miles in 1 hour, then he had to have been exceeding 65 miles an hour at least once during that time period. All right, so keep that in mind. You might have a mathematical judge that knows what they're talking about, and you could get convicted for speeding even though you weren't clocked at a particular speed. Okay, guys, that's it for today.